Hello. In this chapter, we are now going to be talking about chi-square tests for goodness of fit. Basically, this time we're going to be talking about categorical data. Remember how we could talk about the number or the color of cars or something, how many red vehicles are in this parking lot, and we can take that into a percent and figure out how many we're supposed to have. That's where we're headed in this chapter, where we're dealing with categorical data rather than quantitative. The learning objectives for this section, there's 4 of them, and basically we're back to stating hypotheses again, and we're going to compute what we call expected counts. Today we're also going to find the chi-square test statistic, degrees of freedom, and the p-value for a chi-square test for goodness of fit. These other 2 we will use later on in the chapter. Sometimes we want to examine the distribution of a single categorical variable in a population. The chi-square goodness of fit test allows us to determine whether a hypothesized distribution talking about seems valid. Some information that Mars we can decide whether the distribution of a categorical variable differs for 2 or more populations. The company says that the color distribution of M&M's milk chocolate candies on average, we will often organize our data in a two-way table. Should have 13% it's also possible to use the information in a two-way table to study the relationship between 20% orange and different categorical variables. The one-way table summarizes the data from a sample allows us to determine if there's convincing evidence of an association between the variables in the population. In general, one-way tables display the distribution of a categorical variable for the individuals in the sample. So here's our categories, and then we have our count from our sample bag. There were 60 total candies in our sample bag. The sample proportion of blue M&Ms is p hat, 9 out of 60, which was 0.15. Up here, Mars is telling us 24% should be blue. Keep that in mind. That's where we're headed. We're going to see the sample proportion of blue M&Ms was 0.15. True. Since the companies claim that 24% of all M&M's milk chocolate candies are blue, we might believe that something fishy is going on. We could use the one sample z-test for a proportion to test the hypotheses. So our null hypothesis is that the proportion is equal to 0.24, as the company says. We're suspicious, so we're saying, no, we don't think that p is really equal to 0.24. We think it differs. Performing a one-sample z-test for each proportion would be pretty inefficient and would lead to a problem of multiple comparisons. One sample z-test for each color, it wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much from the one claimed by the company. For this, we need a new kind of significance test called a chi-square goodness of fit test. So, in a chi-square goodness of fit test, the null hypothesis should state a claim about the distribution of a single categorical variable in the population of interest. The alternative hypothesis does not have a specified distribution. So, we could write the hypotheses something like this. The null hypothesis is that all of these that the company told us, probability of being a blue, or proportion of blue is 0.24, proportion of orange is 0.2, and so forth. Our alternative is that at least one of these is incorrect. Notice we're stating what we're talking about. We're stating what our P stands for. The idea of a chi-square goodness of fit test is this. We compare the observed counts from our sample with the counts that would be expected if H sub 0 would be true. The more the observed counts differ from the expected assuming that the color distribution stated by Mars Incorporated is true, 24% of all M&M milk chocolate candies produced are blue. For random samples of 60 candies, the average number of blue M&Ms should be 14.4, 24% times 60. That's our expected count of blue M&Ms. Using this same method, we can find the expected counts for other color categories. Let's watch or not. So the chi-square test to show you how they found out all of this. To see if the data gives convincing evidence against the null hypothesis, we compared the observed counts from our sample with the expected counts, assuming H sub 0 is true. If the observed counts are far from the expected counts, that's the evidence that we're seeking. So here's a pictogram or a bar graph of our observed and expected counts. So the purple color right here is the observed, and the red is what the company is telling us we should have received. Notice most of them are pretty far off. We see some fairly large differences between the observed and expected counts of several color categories. How likely is it that these differences, this large or larger, would occur just by chance? That's the question we're going to be asking ourselves today. So to answer this question, we calculate a statistic that measures how far apart the observed and the expected counts are. The statistic we use to make this comparison statistic is a measure of how far the observed counts are from the expected counts. Here's the formula for chi-squared. Notice it's this funky x squared, chi-squared. There's a table in the back of the book that we'll be looking at. It's the sum of the observed minus the expected, the quantity squared, divided by the expected, where the sum is all over the possible values of the categorical variables. So this table shows our observed and our expected. If we take and find all of our chi-squared, notice we took the blue, the observed, minus the expected and squared it, divided by the expected. The orange, the green, the yellow, the red, and the brown. We added those all up. That's the sum. So chi-squared comes out to 10.180. Think of chi-square as a measure of the distance of the observed counts from the expected counts. Large values of chi-square are stronger evidence against H sub 0 because they say that the observed counts are far from what we would expect to be true. Small values suggest the data are consistent with the null hypothesis. The sampling distribution of a chi-square statistic is not a normal distribution. It is a right-skewed distribution that allows only positive values because chi-square can never be negative. When the expected counts are all at least 5, the sampling distribution of chi-square statistic is close to a chi-square distribution with degrees of freedom equal to the number of categories minus 1. So here they're showing you different chi-square distributions. Here's where degrees of freedoms are 1, 4, 8. Notice the higher the degrees of freedom, the closer we are to normal, but notice they're all still skewed to the right. We computed the chi-square statistic for our sample of 60 M&Ms to be 10.180. Because all of the expected counts are at least 5, the chi-square statistic will follow a chi-square distribution of degrees of freedom 6 minus 1, 6 colors minus 1, which is 5. Reasonably well when H sub 0 is true. So this is our chi-square distribution with degrees of freedom of 5. Here's our 10.180. We're looking for this area again, which will be our p-value. To find the p-value, use table C in the back of the book and look for degrees of freedom equal 5 row. And then we're looking for between 0.10 and 0.05, because this, if we change it to a decimal, we're looking between here, so our p-value is somewhere between 0.10 and 0.05. Here's where our chi-square falls, so our p-value is somewhere between these two. So since our p-value is between 0.05 and 0.10, it is greater than alpha of 0.05, therefore we fail to reject, so our p was greater than alpha, we fail to reject H sub 0. We do not have sufficient evidence to conclude that the company's claimed color distribution is incorrect.